All right, so today we're going to talk about some trig identities and using some properties to help verify what we call identities. And we've done this in Algebra 1. It just was a little bit different point of view and how we got it done. And so we'll take a look at those as well. We've worked a little bit with trig identities back in Unit 2, but not the way we should have and not the way we're going to now. So we're going to pick that up starting today, right? So the idea is to be able to verify some trig identities. Before we do that, let's take a look at some algebraic identities. Here's what we mean by an identity. In Algebra 1 class, we gave you this equation to solve. And so you needed to go solve it. And of course, you're going to try to get x by itself. So the first thing you would do here, hopefully, is distribute this 2. You get 3 plus 2x minus 10 equals 2x minus 7. Then you combine like terms here, and you get 2x minus 7 equals 2x minus 7. Now, in Algebra 1 class, you kept going, right? You added 7 to both sides. Then you wanted to collect the x's by subtracting 2x from both sides. And you end up with 0 equals 0, at which point you probably talked about how this was infinitely many solutions or all real numbers because 0 always equals 0. But your first sort of, I know what's going to happen, probably came right here, where 2x minus 7 equals 2x minus 7. That is what we mean by an identity, because in the Algebra 1 class, used to be a while ago, we would stop and call this an identity. And what we mean by that is that there's infinitely many solutions in Algebra 1 class. Here, we're basically saying, you know what, the left side looks like the right side. The left side's always going to equal the right side, no matter what you put in for x. That's why there's infinitely many solutions. So this equation is always going to be true. And so we kind of carry that over and get used to the idea of trying to make the left side look like the right side. And if we do that, we know that we've got an identity and that we're going to have infinitely many solutions, right? So if we're given a problem like this, then really all we have to do is show that the left side looks like the right side. And then we're done, right? So we start simplifying both sides here. We can double distribute the right side or FOIL it, and we get 2x squared minus 6x minus x plus 3. And then combine your like terms there. And then the left side, you're going to double distribute here. We get 2x squared minus 10x plus 3x minus 15, and then plus the 18. And then combine your like terms here and here, and we get 2x minus 7x plus 3. And as you can see, the left side looks like the right side. So we can continue trying to get x by itself, but what we're going to find is that we're going to get 0 equals 0. So we're going to have infinitely many solutions because this is what we call an identity, right? And we've kind of shown that. Well, in trig, that's what we do, right? We try to verify that an equation is an identity. We try to verify that the left side actually is the same as the right side. And so we're basically going to simplify the equation down to where we can see that. Okay? Now, to do that, we need to understand that there are some things that we can rewrite. And we've seen these before, the reciprocal identities. That's what reminds us that tangent and cotangent are reciprocals of each other. So I can always rewrite cotangent as 1 over tangent, or I can always rewrite tangent as 1 over cotangent. And we do that in hopes of trying to simplify an equation, right? Same thing with secant and cosine. They're reciprocals of each other. And same thing with cosecant and sine. We also had some quotient identities that said that the tangent of an angle can be rewritten as sine over cosine. Cotangent can be written as cosine over sine. We've got some more. There were some Pythagorean identities that we looked at before. And it kind of comes from the idea of the Pythagorean theorem or the equation of a circle, all of which we looked at in Unit 2. But basically, if we take the sine of an angle and square it, take the cosine of an angle and square it, and add those two together, we should always get 1. So sine squared plus cosine squared is always going to be equal to 1, which means that we can replace sine squared plus cosine squared with 1. Okay? We had some others. Tangent squared plus 1 is equal to secant squared. Those are the same, so we can always replace them. And then 1 plus cotangent squared equals cosecant squared. Now, one thing that we talked about before when we looked at these is that understand that we can rewrite these. We can rework them a little bit. And what I mean by that is I know that if I can subtract sine squared from both sides of this equation. If I do, this equation turns into cosine squared theta equals 1 minus sine squared theta. Now what that means is anytime I see a 1 minus sine squared, I can always replace it with cosine squared. And then we can always subtract cosine squared from both sides and end up with sine squared theta equals 1 minus cosine squared theta, and the same thing ends up being true. The same with the other two equations here. I can subtract tangent squared from both sides, and if I did, this equation would look like 1 equals secant squared theta minus tangent squared theta. Or I can subtract the 1 from both sides, and it would look like tangent squared theta equals secant squared theta minus 1. Same thing with the last equation. If I subtract cotangent from both sides, then 1 would be equal to cosecant squared theta minus cotangent squared theta. Or subtract 1 from both sides, and cotangent squared theta would be equal to cosecant squared theta minus 1. And we can use these to replace things. Okay? All of these identities, including these guys, the negative angle identities, whoop, too far. This is the whole even and odd conversation. But we can always replace a negative sine theta with sine of negative theta, right? We can always replace any of these. Okay? But these identities you don't have to memorize. We'll give them to you on quizzes and tests. You just have to recognize them and be able to use them and rewrite stuff. Okay? So let's go through and prove some of these trig identities. When we do that, there are some things to keep in mind that might help us along the way. First of all, you're going to have to know your identities. I didn't say memorize, just know them. Learn them and know them and be able to use them. Okay? When we get going, we're going to end up simplifying an equation. And we're going to want to simplify one side. We're only going to work one side. Work on one side only. And so you're going to have more options in terms of simplifying if you choose the more complicated side. Okay? Sometimes if you get stuck, it's helpful to rewrite anything in terms of sine and cosine. Everything can be rewritten in terms of sine and cosine. That might help. Also understand that with these trig functions, you can add them, you can subtract them, you can multiply them, and you can divide them. Sometimes you can even factor them. And it's going to be helpful to do some of those. Okay? You also want to always, since we're going to work on one side, we're only going to simplify one side. You want to kind of keep track of what is on the other side so that you know what you're trying to get to. So you know what your left side should look like or your right side should look like compared to the other guy. And then if a fraction contains 1 plus sine or 1 plus cosine, then you might have to end up multiplying by the conjugate, right? We'll get to that more when we come across it, right? But the conjugate is just going to be the same binomial, only a different sign. And the reason why we would do that is that we'll create an identity for us. We'll see that later. Okay? So just some things to keep in mind that you'd probably want to try to do. Okay? So, first one here. We want to rework one side. Well, the more complicated side is obviously the left side. So let's simplify the left side. And to simplify, the first thing that I would recognize is that cotangent squared x plus 1 feels like it's an identity. It's one of the identities that we just took a look at. Right? And as a matter of fact, it is. It's that third one. 1 plus cotangent squared or cotangent squared plus 1, either way, is going to give you cosecant squared. So I can replace that cotangent squared plus 1 with cosecant squared x. Then I can replace the cosecant squared x with 1 over sine squared x. Right? That's how that works. Cosecant x is the same as 1 over sine x. If I square cosecant to get cosecant squared, I've got to square this side also, which means squaring the numerator and the denominator, so you get 1 over sine squared. Okay? Which works out because now I can divide out the sine squareds, and I get 1 equals 1, and I've verified that that's an identity. The left side looks like the right side. Okay? That's how this works. Next one looks like this. Choose a side that seems more complicated. The right side definitely seems more complicated. Right? So, what do we want to do? Well, probably want to distribute, right? That's kind of what we want to do all the time. So if you distribute, you get cosecant theta, cosine theta, plus cosecant theta, sine theta. Now what? Well, I'm not sure. I'm kind of stuck. So I want to rewrite everything in terms of sine and cosine. Cosecant is 1 over sine. So we can get 1 over sine theta times cosine theta. And this guy is 1 over sine theta. If you do that, you multiply into the numerator cosine theta over sine theta plus sine theta over sine theta. Well, obviously, anytime you divide something by itself, you're going to get 1. So that's plus 1. Cosine over sine is definitely cotangent theta. And keeping an eye on the left side, that's exactly what we wanted the right side to look like. So we have verified that identity. Okay? So it's just rewriting and simplifying and kind of a puzzle, right? We're trying to fit this puzzle together. How do we make the left side look like the right side? Okay? Next one. Well, left side looks more complicated. Since we just distributed and that worked out pretty well for us, maybe we do that again. So we get cosine theta, secant theta, plus cosine theta, cosecant theta. We're trying to look like 1 plus cotangent. Well, after we distributed last time, we wrote everything in terms of sine and cosine, so that's probably going to be helpful again. So you get that. Cosine over cosine is just 1. Cosine over sine gives you cotangent, and so we're right back where we were in the last problem. 1 plus cotangent theta, and we verified that. Okay? All right. Next one. Left side and right side, which one looks more complicated? Left side definitely does. It's got more stuff in it. When you got more stuff, that means there's more things that you can do to simplify. Right? And it's really however you see this. We got to make the left side look like tangent squared. We're trying to get to tangent squared. So one thing we can do is rewrite tangent into sine over cosine. Not always the first step you want to do, but definitely one that can be helpful. We do that, we can multiply this sine into that fraction and get sine squared theta over cosine theta all over cosine theta. I'm trying to get this to look like tangent squared. We're kind of almost there. We got sine squared in the numerator. Now we can introduce the idea of taking this denominator, making it a fraction. Anytime we divide by a fraction, we're actually multiplying by the reciprocal. So we can actually flip this over and multiply it into the numerator. When we do, we multiply straight across, we get sine squared theta over cosine squared theta. And sine squared over cosine squared definitely is tangent squared. And so we verified that identity. Okay? Hopefully this is making a lot of sense. We've got some more that we'll look at together, just all kinds of different strategies. Anytime you see a strategy in one of these problems, you want to kind of carry that with you and maybe try that on one of your future problems. Right? All right, left side, right side. Left side definitely looks more complicated. Oh, by the way, these notes are jumping around. Keeps you from working ahead. Okay. What do we want to do first? Well, we could write this in terms of sine and cosine. So we get cosine squared theta over sine squared theta plus cosecant is 1 over sine. The reason why I would do that is so that the signs would divide out. Cosine squared over sine squared is actually just cotangent squared. So we get cotangent squared plus 1. And then, like I said, anytime you've got something squared plus a 1 or a minus a 1, it's going to just feel like an identity. And as a matter of fact, it is. Cotangent squared theta plus 1 is the same thing as cosecant squared theta. And so I can rewrite that as cosecant squared theta and know that I'm done. Okay? So as instance, we're going from cosine to sine, cosine and sine over to another trig function helped. So sometimes you need to do that. Okay? Next one. Left side looks more complicated. So let's work with that. My first instinct is to go ahead and rewrite all of these in terms of sine and cosine. And so you get that. Now we can multiply the numerator together and get cosine theta over sine squared theta over 1 over cosine theta. We've already seen this once, but we can take this denominator, flip it over, and multiply it into the numerator. When we do, we get cosine squared theta over sine squared theta, which is just going to give you cotangent squared theta. Right? And that's been verified. Awesome. A couple more we haven't seen yet. Here's the next one. Oh, cosine cubed. That looks pretty complicated. But there's more stuff on the left side, so maybe we start there. Now, first time we've seen the fact that there's two terms on the left side, and they both have a cosine theta in them. So we can actually factor that cosine out as if that were an x plus or an x minus xy or whatever. Factor out a common factor. So we'd factor out a cosine theta. When we do that, this works just like it does when you did it in algebra class. I'm going to pull a cosine theta off of cosine theta, and if I do, I have to leave a 1 behind. I take this cosine theta off, and I'm left with sine squared theta. Now, 1 minus sine squared, again, feels like an identity, and it is. 1 minus sine squared is the same thing as cosine squared. And cosine squared times cosine is cosine cubed. And that's what we're trying to get to. Okay? So sometimes you need to factor out. Last one. and see if we can't pick up a new strategy from this guy. Okay, left side, right side. The left side seems to have more stuff in it, so maybe I want to go there. Right? How do I make that look like the right side? Well, what if we rewrite this, not in terms of sine and cosine, but make that 1 over tangent squared x. Then we distribute. We get tangent squared x plus 1. Okay, to make it look like the right side though, right side's a fraction, it's got 1 minus sine squared in the denominator. So I wonder if I need to, I can't just turn that into secant squared because it's not going to help. So how about I just rewrite this as sine squared x over cosine squared x. Then we've got to get common denominators for these guys. This guy has a denominator of 1, so he needs to have a denominator of cosine squared. So we get sine squared x plus, over cosine squared x plus cosine squared over cosine squared. Now I do that so that I can actually combine those two fractions. And so we're going to get sine squared plus cosine squared over cosine squared. And we're supposed to make it look like 1 over 1 minus sine squared x. Now, we're getting closer because this numerator is a 1. That's an identity. But now you have to be a little crafty. Cosine squared we get if we take 1 minus sine squared. If we subtract sine squared from both sides from that 1 identity. So I can actually, this is a situation where I want to take the single term and turn it into 2 terms, right? Make it a little bit more complicated looking to make it look like the right side. That's me paying attention to the other side to know what my identity needs to look like, but that works. Okay? All right. And so that's as many strategies as I can get for you right now. We'll pick up some more next time, but use that with your homework, and we'll go over that next class.